Okay, welcome to the Unit 2, Day 14 notes. We're looking to analytically find the derivative of a polynomial, polynomial type, sine and cosine functions. So, the first example, consider the function f of x equals 3. It's a constant function. What does the graph of this function look like? If a tangent line were drawn to f of x at any value of x, what would the slope of that tangent line be? So here I have the line in green, y equals 3. So that's what the function looks like. It's a horizontal line. And then what is the slope of any horizontal line? That's 0. So again, if I pick any point right here, tangent line is going to be on that, but its slope is 0 right here. Tangent line is going to be 0, 0. So what we find out is the slope of any tangent line drawn to the graph of a constant function would be 0. So that answers this based on this thought process. If f of x equals c, where c is any constant, then f prime of x, or the derivative of f of x, equals 0. Okay, again, slope of any tangent line drawn to the graph of a constant function would be 0. So next on page 1 we have a chart, and we have 6 different polynomial or polynomial type functions, and I'm going to find the derivative of each function, and we're going to see if we can figure out what the algorithm is that I use in finding for each function. So we've talked about it a little bit, but let's see if we can figure it out. All right, so I'm giving you the derivative. Let's do these first 3. And hopefully we know that that's x to the first. And really any constant's really understood as x to the 0. So, and we could do this using the difference quotient. F of x plus h minus f of x all over h is the limit as x approaches 0. And we could go and find what this is. And we did a bunch of those. So, hey, I start to see a relationship. Hey, 6, 2 times 3 is 6. And then it goes from x squared to x. Let's try that. 1 times 2 is 2, and then it goes 1 less. And x is 0. 0 times 3 is 0, so everything's 0. Same thing here. 3 times negative 5 is negative 15, and it's 1 less. 2 times 2 is 4, and the degree is 1 less. Because again, that's understood to be degree 1. This is understood to be 1. 1 times negative 3 is negative 3, and 1 less is x to 0, which is just 1. And then a constant, we just said before, the derivative is 0. Here, derivative of a constant is 0. Then I go 3 times negative 3 is negative 9. 1 less for a degree. 4 times 6 is 24. And that's x to the third. Try these last 3. A little bit harder because we have some negative exponents. And we also had some rational exponents as well. So later on, when we're simplifying these, we'd have to get rid of the negative exponents. But for what we're doing now, again, let's see if the rule works. Negative 1 times negative 2 is positive 2. 1 less in the exponent. So negative 1 minus 1 is negative 2. Negative 2 times positive 3 is negative 6, goes to x to the negative third. So 2 thirds times 6 is 4. 2 thirds minus 1 is negative 1 third. Negative 2 times 4 is negative 8. Minus 1 is negative 3. Negative 1 half times negative 6 is 3. Subtract 1 is negative 3 halves. And then 1 half times 3 is 3 halves. Subtract 1 is negative 1 halves. On the bottom there it just says, based on what you've seen in the table above, you should now be able to infer how to complete the following power rule for differentiation. So this is the power rule. What we have here is this d dx is our differential operation. And let me write, so we've been talking about f prime of x, and this is another way of writing it, d dx. So the differential operation. So our power rule says take what the exponent is, put it up front. If there was a constant there, you'd multiply it by the constant, and then the exponent becomes 1 less. So this is going to be our first rule of differentiation. In order to apply the power rule for differentiation, the equation must be written in polynomial form. What does suppose polynomial form refers? So functions in polynomial form if it is a sum and or difference of multi-monomial terms. So I have an example here, generic example. I'll do a specific one. So I could have, and again, the a, b, c, d just represents either the coefficients or the constant. So I could have 8x to the fifth minus 7x to the fourth plus 2x to the third. And again, the BC, that just says they can be different. They don't have to be different. Again, I could have minus 7x squared plus 12x minus 15. and that'd be a polynomial. So the next examples want us to find the derivative, f prime of x, for each of the following functions. Leave your answers with no negative or rational exponents and as a single. Let's try that again. So with no negative or rational exponents and as a single rational function when applicable. So the first thing I'm going to do is rewrite it. So I get f of x equals 2x to the negative 2 minus 4x cubed. Now I'm going to take the derivative, and I can take the derivative of each separate term. So f prime of x equals, and I'm going to take the exponent, negative 2 times 2 is negative 4. It's going to be 4x to the negative third. Exponent 3 times negative 4 is negative 12, and I'm going to go down by 1. Okay, I can't leave it like this. So f prime of x equals negative 4 over x cubed minus 12x squared. Now I want to write it as a single rational function. So what am I going to do? I'm going to multiply this by x cubed over x cubed to have like denominators, and my final answer is going to be negative 4 minus 12x to the fifth all over x cubed, and that is my derivative. So why don't we try these? I'll write them up, take a few seconds to try. And again, first rewrite it, and then take the derivative. Okay, here's the first four. When you pause it, write these down if you haven't already tried it, and just make sure you understand how you got each step. Otherwise, make a mark and we can talk about it. And again, we're using the power rule here. Okay, so here's the final two. Again, double check the steps that I did to rewrite it up front and simplify, and then take the derivative and then rewrite it using radicals. Okay, so this will be the end of part one.